Hi, this is Nick Fryer, and today we're talking about the Physics Lab 4, which has to do with oscillations of a spring mass system. So, just as an introduction, we have two goals of this experiment. The first is to compare observed and predicted motion of a spring mass system that moves in two dimensions. And our second is to plot the changes in kinetic, gravitational potential, and spring potential energies and just see how they kind of match up with each other. Just as a preview, our predicted motion did closely match the observed motion, but the model predicted some different changes in position. And the change in total energy is zero, as well as individual energy changes adding up to zero. So just some basic concepts. First, just like Lab 3, we have Newton's second law of motion, which says that the net force on an object is equal to the time derivative of velocity or of momentum. And this can be rearranged to find our velocity and position update formulas, just like Lab 3. We also, most importantly, are working with the energy principle, which says that the change in energy of a system is equal to the work done by the surroundings of the system plus the transfer of energy between system and surroundings. So in this case, heat, which is Q. Here we have three different energies that we're working with. So kinetic, gravitational potential, and spring potential energies, and their formulas can be shown here. So our system we consider to be the mass that's on the spring, as well as the spring and the earth, which exerts gravitational force. And in this case, we have no surroundings. We kind of just put everything into the system. They're all conservative forces, so we can do that, and it makes our calculations a lot easier. We can say that the work done by the surroundings is zero because there are no surroundings, and there's no energy transfer because, again, there's no surroundings. And this results in the equations that you see. So our delta E of the system, which in this case adds up the three energies I talked about before, has to equal zero. So this is the tracker analysis of the video that they gave to us in pre-lecture number 52. It is a little blurry, but you can see that the tracker, which in this case is an auto tracker, is pretty accurately measuring the mass as it goes from side to side and up and down. So this is just brief tracker data. We got 0.095 seconds per frame, and the mass was given to us to be 0.402 kilograms. The initial time that I started recording was at 0.38 seconds, and I ended at 9.687 seconds. And my initial position and velocity can be shown here. Note that the velocity starts at rest because I started recording as soon as he released the mass. So just as some initial conditions, again, the mass is given to us, and then I just put in the position and velocity vectors that you see there from the data that I got, and the delta T, again, from what I got, 0.095 seconds. We also have some constants, so G, and then the spring constant, as well as L naught, so the relaxed length of the spring. These can all be obtained from these formulas that you see here. So in the T oscillation, that's from our period, which we'll talk about later. We can plug in the mass and calculate for K. And then, for F net in the Y direction, we have minus mg plus our spring force in the Y direction, which has to equal zero. And then we can calculate K. And these are the relevant equations for the glow script model. This, again, comes directly from the formulas that I showed before. These are the iterative steps that I do, kind of just plugging everything in, making sure that everything is of the formula that it needs to be. And then at the end where it says count equals count plus one, that section is to be able to compare our video measurements from our model measurements. So this is kind of just a quick visual of what the glow script model can do. It generates kind of a helical pattern, and it gives us a bunch of different graphs, which we can see right here. So we have change in energy versus time, as well as X position and Y position versus time. You can see that the UG and US, so gravitational and spring potential energies, have similar magnitude, but they have opposite signs and they oscillate. So as one increases, one decreases. The delta K, so the kinetic energy, also oscillates, but it has less of a magnitude, and it's kind of just used to offset the difference between the magnitudes of the other two. As far as the position versus time graph goes, you can see that the amplitudes in the experiments and the magnitudes are a little bit higher than the model, and the model predicts the crests and troughs to come a little bit later than the experiment shows, and that's for both X and Y positions. Just some quick sources of error. We don't account for other forces like air resistance and drag, as well as other energies like thermal and sound energies that could play a part, and our tracker measurements could just be inaccurate. So what does it mean? Is the energy principle satisfied? Yes, it is. Everything adds up to zero as it should, and so our energy principle is conserved here. As far as periods of oscillation, we can calculate each period individually from crest to crest or trough to trough, and then average them out. And we get these X and Y periods that you see here with a somewhat small difference. And these are just caused by tracker inaccuracies and unaccounted for forces. And this can impact calculating our K, our spring constant, or spring force and potential energy.